So, this is lecture 8 of the course on fundamentals of transport processes. Welcome to you all, and we will continue what we were doing in the previous lecture, that is on kinematics. This is the description of fluid flow without reference to the forces that are acting on the fluid. In the case of heat and mass transfer, there was a concentration or a temperature field and there was a flux. That flux can the flux is a vector, it can be directed in any direction in space. However, it has just one direction. In the case of fluid mechanics, we have a velocity field and that velocity field itself has a direction. The transfer of momentum, okay, there is a direction associated with the momentum itself, there is a direction associated with the direction of transfer, and these two things come together. So, in that sense, fluid mechanics is a little more complicated than normal heat and mass transfer, and for this reason in the past few lectures we have been conducting preparatory lectures on vectors and tensors, their derivatives, their integrals. Okay. So, let us just briefly review that before we continue our discussion on kinematics. For any kind of flow, say a pipe flow or flow around a particle and so on, we have a 3-dimensional coordinate system. The velocity in this 3-dimensional coordinate system is a vector. It is a vector field, it is defined at each point within the flow. It has a direction and a magnitude, and both of these can vary both in time as well as in space. The direction and the magnitude of the velocity can vary both in time as well as in space. We do analyze these of course in a fixed coordinate system with their components in those 3 coordinates, but however, this velocity field itself, as I have been trying to emphasize, has an identity which is independent of the underlying coordinate system. The flow in a pipe, for example, will continue to flow in that same direction regardless of what coordinate system I use to analyze that flow. Okay. So, we are looking at certain fundamental things about these vectors, okay, which are invariant under coordinate systems. The magnitude and the direction are 2 such in fundamental independent quantities. The dot product of 2 vectors is an independent quantity. For example, the dot product of 2 vectors A dot B, even though I can write it in a coordinate system as A1 B1 plus A2 B2 plus A3 B3, this dot product is independent of the coordinate system that you use to analyze. It depends only upon the vector. Similar is the thing with the cross product A cross B, which with reference to a coordinate system, I had already shown you that this can be written as epsilon I j k A j B k. Resultant is a vector. There is one free index I, which gives the direction of the resultant cross product. J and k are repeated, so they represent dot products. This once again is independent of the coordinate system that is used. Specifically in the context of derivatives of vectors, we had defined 3 such. One was the gradient, okay. Gradient of the velocity field, which I can write it as partial by partial x I of velocity j. This quantity has 2 unrepeated indices. So, there are 2 directions associated with this quantity. Therefore, it is a second order tensor. There is one direction associated with the direction of the gradient, the direction in which you are measuring variations. There is a second, which is the direction of the velocity, the direction in which the fluid is moving. So, there are these 2 directions associated with it. This is a second order tensor, which has an identity once again independent of the coordinate system that you are using to analyze the problem. Okay. There were other derivatives that we had analyzed. One of them was the divergence del dot u, which is the divergence of u. In indicial notation, you would write that as partial ui by partial xi, okay, divergence of a vector. Okay. And by an example I had shown you in the last lecture that this is non-zero at a point only if I have a velocity component that is diverging radially outward from that point. Okay. Only if I have something that is diverging radially outward from this point. In other words, if I sit at this particular location, okay, and I put in a coordinate system at this particular location, and the distance from the origin, that is the distance from the point at which I am sitting, is r, and if the velocity has a component that is along the vector from the origin, then the divergence will be non-zero, okay, because you know from the integral theorem for the divergence that integral ds n dot u is equal to integral dv divergence of u. Okay, integral ds of u dot n, that is, let us just expand this volume out a little bit. Okay. This is the point that I am sitting at, and I have a small volume around this point. That surface has its unit normals, and then I have the velocity vector, which is in general in some direction. If I take that velocity vector dotted with the unit normal integrated over the entire surface, I get the net amount of fluid that is coming out of that surface, the volume per unit time that is coming out of this surface. So, only if there is a net amount of fluid coming out of this surface will I have the divergence of u being non-zero within this surface. Okay. So, that is a physical implication of the divergence. And the other vector that we had defined was the curl del cross u, which is epsilon I j k partial by partial x j of u k, the velocity. Okay, that is the curl of the velocity vector. Okay. And in the last lecture, I had shown you in a simple example that this curl of this velocity vector, okay, over some curve, over some line in this 3-dimensional space will be non-zero only if there is circulation around this point. Okay. We had seen it in the last lecture by taking a velocity vector which is a solid body rotation, and we had calculated the integral, the del cross u for that particular solid body rotation, okay, with two different components of velocity. And we saw that the vorticity, which was equal to the curl of the velocity, is non-zero only if there is a circulation around that point. Okay. And that vorticity is related to the angular velocity of that solid body rotation. There is an integral theorem for that, okay, which states that integral over any surface of n dot del cross u. N dot del cross u is just the unit normal dotted with the vorticity vector. Note that the vorticity vector is equal to the curl of the velocity vector. It is a vector and it is equal to the curl of the velocity vector. Obviously, it is in a plane perpendicular to the velocity, because when you take the cross product of two vectors, you get a resultant that is perpendicular to both of those. So, this vorticity vector is in a plane perpendicular to the velocity vector, and this integral of the unit normal dotted with del cross u over any surface is equal to integral, the line integral of dx dot u. So, I take this little differential element on the surface, that is dx vector, and dot it with the velocity vector at each point, and then take the integral over the entire contour. That is equal to n dot del cross u over any surface for which this contour is the perimeter. It is equal to n dot del cross u for any surface for which this contour is the perimeter. Okay. So, those are the physical representations. Last class I had also told you that whenever the curl of a velocity is equal to 0, that velocity can always be represented as the gradient of a potential. So, that is the velocity potential. So, when del cross u is equal to 0, u can be written as the gradient of phi. When the divergence of the velocity is equal to 0, the velocity can always be written as the curl of a vector. Okay. When the divergence is 0, the velocity can be written as the curl of a vector. Does not simplify things, because velocity also had 3 components and this vector now has 3 components. Significant simplification results when you have 2-dimensional flows with only 2 components, u1 and u2. In that case, the vector whose curl you take to get the velocity has to be perpendicular to the plane. Okay. So, that we are defined as the stream function vector with direction perpendicular to the plane. So, that basically defines the stream function. Okay. And I had shown you that along lines of constant stream function, the velocity vector is tangent to lines of constant stream function, and the difference in stream function between adjacent lines of constant stream function called streamlines is equal to the net flow through that surface. An important concept which we will discuss now is the rate of deformation tensor. Okay. I had started off the discussion for you in the last class. The rate of deformation tensor is the gradient of the velocity. Okay. I had written it for you in the last class as partial ui by partial xj, where I is the direction of the velocity, j is the direction in which you are taking the derivative. Okay. So, the direction of derivative means that you go a small distance in that direction, find the change in velocity and divide it by the distance traveled. Okay. And as we saw, it has different components, partial u1 by partial x1, it has 9 components. So, first thing is the velocity itself has 3 components at any position. This is the velocity, it has 3 components at any position. And then I can go a small distance, delta x. This distance traveled can also be in one of 3 directions, and then I find out what is the velocity at this other position. Note that I am traveling in space while keeping time a constant. So, at a given instant I am traveling a small distance in space and seeing how the velocity changes. Okay. So, this is the velocity vector. I will just write it separately. This is u at x. The velocity vector that I get at the new position u at x plus delta x is in general slightly different than that at u of x. So, I will get u at x plus delta x minus u of x, okay, which is the difference in velocity. So, the difference in velocity is this one, delta u, okay. That is equal to delta x dotted with the gradient of u. Okay. So, this I can write it, for example, as delta x I. So, I should write it, be careful here. Delta x j times partial u I by partial x j. So, there is a difference in velocity, that is delta u I is equal to delta x j times partial u I with respect to x j. Right hand side, one repeated index, dot product, free index is I, it is the same as the one on the left hand side. So, this thing, this second order tensor here contains all the information about how the velocity is changing as I move a small distance away from a given location in space. Okay. Note that this partial u I by partial x j is a function of position. it varies as you go to different points in the velocity field, but it is not a function of the distance traveled from that point, okay, from the definition of the gradient. The gradient definition basically states, if I start at some particular point and move a small distance delta x from that point, the difference in a quantity, whether it is a scalar or a vector, is going to be equal to delta x dotted with the gradient of that quantity, provided delta x is sufficiently small in the limit as the length of delta x goes to 0. Okay. So, therefore, this gradient of the velocity is something that is defined at each point in space. It is dependent upon position. It could depend upon time, because velocity itself is changing with time. It does not depend upon delta x. Okay. So, it is a function of the velocity field itself. So, if I am sitting at some particular location, I can always find out how much the velocity is changing as I go to nearby locations. So, in a similar manner to the temperature gradient, it gives me the direction in which the temperature is changing. Okay. As you go to sit at one location and go to nearby locations, it tells you how the temperature is changing. The other thing it is telling you is that if two nearby points, okay, if I have two nearby points here, okay, if I have two nearby points here and I wait some time delta t, okay, if I wait some time delta t, right. So, if I have two nearby points and if I wait a time delta t, this distance that this point travels, the distance that this point travels is going to be equal to u at the location x times delta t. So, the distance that the first point travels, the point at the location x travels, is going to be u at x times delta t. The second point here is going to travel some other distance. Okay. The second point here is going to travel the distance u at x plus delta x times delta t. Okay. So, therefore, the change in this displacement vector between these two locations, the change in the displacement vector between these two locations is going to be equal to u at x plus delta x minus u at x times delta t, okay, which is equal to grad u delta x j partial u I by partial x j times delta t. Okay. So, this line element delta x j has changed by an amount equal to partial u I by partial x j times delta t when you have traveled this distance. So, this basically tells you how the distance between two nearby points within the fluid is changing as time is evolving. Okay. And since all stresses which are exerted on the fluid depend only upon the rates at which nearby points are changing their distance, it is this gradient of the velocity vector which basically determines the stress in a fluid. Okay, and that is the reason it is important. Now, this velocity gradient is a second order tensor. It has 9 components, okay, and you can of course write down the components in different directions. However, there is a fundamental way in which you can classify deformation on the basis of how this rate of deformation tensor, what are the fundamental invariant components of this rate of deformation tensor. Okay. Let me just explain that a little bit. Okay. So, in the previous lecture we had started that. Okay. So, my is equal to partial u I by partial x j. Okay. It has a total of 9 components. For the purposes of the present discussion, I will restrict attention to a 2-dimensional velocity field, some velocity vector u in this 2-dimensional velocity field. We will see later how this is extended to 3 dimensions, but it is easier to visualize if I do it in 2 dimensions. Okay. So, in 2 dimensions there are 2 coordinates and 2 velocities, and therefore, this gradient of the rate of deformation tensor has only 4 components. Okay. Now, this any matrix of this kind, these are always square matrices, because in 2 dimensions it is 2 by 2, in 3 dimensions it is 3 by 3. So, they are always square matrices. Any matrix can be written as the sum of a symmetric and an antisymmetric matrix. Okay. So, this can always be written as the sum of a symmetric matrix and an antisymmetric matrix, okay, where Sij is equal to partial ui by partial xj plus whole transpose, okay, that is half the sum of the matrix plus its transpose, okay, the sum of the matrix plus its transpose, and Aij is equal to half of partial ui by partial xj minus partial ui by partial xj the whole transpose. Okay. What does it mean to take the transpose? Okay. So, in this matrix I was representing the row indices, okay. This I was representing the row indices, I is 1 is the first row and 2 is the second row, j represents the column index. Okay. When you take the transpose, you interchange the row and the column indices. Okay. So, in the transpose of the matrix, if the original matrix had an element m 1 2, in the transpose that element would go into the location m 2 1. So, you are interchanging the row and the column. Since I represents the row index and j represents the column index, the transpose just corresponds to interchanging the row and the column, that is the second one I interchange the row and the column. So, I get partial uj by partial xi. Okay. Similarly, for the antisymmetric tensor, and you can easily verify that if I take these two and add them up, if I take these two and add them up, the symmetric and antisymmetric, I get back to this tensor. Okay. So, I have separated out the rate of deformation tensor in this simple 2 dimensional system into a symmetric and antisymmetric part. Okay. I can further separate out the symmetric part. Okay. So, the symmetric part, if I write it out, Sij is equal to half partial ui by partial xj plus partial uj by partial xi. Okay. So, this has components partial 1 by partial x 2 . So, this is the symmetric matrix, okay, and I can further separate it out into 2 parts. One is what is called an isotropic matrix. Okay. The isotropic matrix has as its diagonal elements the trace of this matrix divided by 2. Okay. So, this I can write it as half So, that is the first part. Okay. You can easily identify this. This can also be written as half of partial u 1 by partial x 1 plus partial u 2 by partial x 2, this scalar quantity times the identity matrix. Okay. So, that is the first part. Okay. And there is a second part which is basically the original symmetric matrix minus the one that I already have here. Okay. So, this will be partial u 1 by partial x 1 minus half then this partial u 2 by partial x 2 and I should have made a mistake here. Okay. So, this is the matrix that is left over once I have taken out this half of this, I have taken out this isotropic matrix. Okay. And this thing is what is called the symmetric traceless matrix. It is called a symmetric traceless matrix, and this first one is an isotropic matrix. Okay. The first one is an isotropic matrix. Okay. So, this is equal to half. You can very easily see that partial u 1 by partial x 1 plus partial u 2 by partial x 2 is the divergence of the velocity in 2 dimensions. Okay. So, this is the divergence of the velocity in 2 dimensions. Okay. So, this is divergence of velocity times the identity matrix. Okay. The identity matrix is delta I j, and the second is this symmetric traceless matrix. This matrix, okay, which I have written out in long form here, it has the property that the trace is equal to 0. The trace is the sum of the diagonal elements, and you can easily verify that if I add up the 2 diagonal elements here, I will end up getting 0. Okay, if I add up the 2 diagonal elements here, I will end up getting 0. So, this is a traceless matrix, okay, and the second matrix is an identity matrix. Okay. So, therefore, I have separated out my rate of deformation tensor into 3 parts. Okay. One is the antisymmetrics plus the symmetric traceless plus an isotropic matrix, which in 2 dimensions is half divergence of u into delta I j. Okay. So, one can now ask the question, what types of deformation do each of these represent? Okay. So, if you recall, we had in 2 dimensions we have a 2 by 2, that is 4 terms in the matrix. Okay. The antisymmetric matrix has only one independent element, because the diagonals are 0 and the off diagonals are equal to negative of each other. The isotropic matrix has only one element. The symmetric traceless matrix, in addition, has in general has 2 independent elements. The sum of the diagonal elements has to be equal to 0, okay, for the symmetric traceless matrix. So, let us look at the type of deformation that each of these represents. Okay. So, first let us look at the isotropic. Okay. So, therefore, if I am sitting at one particular location, okay, note, okay, then for the difference in velocity, this is x 1, x 2, I have delta u 1, delta u 2, the 2 components of the velocity is equal to this matrix times the distance I have travelled. Okay. So, the difference in velocity between 2 locations is equal to the gradient of the velocity times the displacement travelled. Okay. For an isotropic matrix, I have only 2 diagonal elements which are non-zero, and they are both equal. The off diagonal elements for the isotropic matrix are 0. Okay. So, let me just for simplicity call the diagonal elements of this as S, and the off diagonal elements are 0. Okay. So, this is the kind of deformation I will get, difference in velocity when I travel a small distance delta x 1, delta x 2 in the 2 directions for an isotropic matrix. So, you can easily simplify this to get the velocity difference delta u 1 is equal to s delta x 1, delta u 2 is equal to s times delta x 2. Okay. So, if I travel a small distance delta x 1 in the plus x 1 direction, if I travel a small distance delta x 1 in the plus x 1 direction, okay, then my velocity vector delta u 1 is equal to s into delta x. Let us call this delta x. If I travel a small distance delta x in the plus x 1 direction, delta u 1 is equal to s times delta x, delta u 2 is equal to 0, because I have not travelled in the x 2 direction. So, I get a velocity vector that looks like this, okay, at this location. If I travel a small distance in the plus, okay, if I travel a small distance delta x in the plus x 2 direction, then delta u 1 is equal to 0, delta u 2 is equal to s times delta x. Okay. Delta u 1 is equal to 0, delta u 2 is equal to s times delta x. Okay. That is the velocity vector. This is the relative velocity vector of this point relative to the origin. Okay. I am always taking the difference in velocity delta u 1 and delta u 2 between a nearby point and the origin. Okay. Similarly, if I travel in the minus x 1 direction, delta u 1 is equal to minus s delta x, because delta x is now negative, delta x 1 is equal to minus delta x. Therefore, delta u 1 will be in the minus delta x 1 direction. Similarly, over here. In fact, this was exactly the velocity profile that we had solved in the previous lecture. Okay. If you recall, we had said that u r is equal to some constant times r and u phi is equal to 0. Okay. So, if you these are at the along the coordinate axis, okay, but if I draw a sphere around this, okay, and I calculate the velocity at various points, you find that the velocity due to this isotropic part is radially outward. Okay. So, the velocity profile due to this isotropic part of the rate of deformation tensor is always radially outward. Okay. No surprise, because this coefficient here s was equal to the divergence of the velocity field, and I told you that the divergence is non-zero only if there is a radial outward or inward flow. If there is a radial outward flow, then the divergence is positive. Fluid material points are moving outward relative to the center. Okay. If it is negative, they are moving inward towards the center. Okay. So, there is a net volume of fluid that is coming out, okay, and that can come out only if there is a source at the origin. Okay. So, this isotropic part is related to the outward or inward flow radially, okay, away from the origin or towards the origin. Okay. So, this is just one part of the rate of deformation tensor, the isotropic part. Next, let us look at the antisymmetric part. Okay. Next, let us look at the antisymmetric part. Okay. So, for the antisymmetric part, delta u 1, delta u 2 will be equal to some deformation tensor times delta x 1 delta x 2. This tensor is antisymmetric. So, in general I can write this as 0, minus a, and 0. Okay. So, this is an antisymmetric tensor times delta x 1 delta x 2 gives me the relative velocity with which nearby points in the fluid are moving. Our coordinate system once again. Okay. And if I move a small distance in the plus, okay, so therefore, this gives me the velocity delta u 1 is equal to minus a delta x 2, delta u 2 is equal to a delta x 1. Okay. So, delta u 1 is minus a delta x 2, delta u 2 is equal to a times delta x 1. Okay. If I move a small distance delta x in the plus x 1 direction, delta u 1 is equal to 0 and delta u 2 is equal to plus a times delta x. Okay, so, delta u2 is in this direction. Okay, so, the velocity vector at this location will be in the plus x2 direction. Okay. If I go a small distance delta x in the plus x2 direction, then I have delta u1 is equal to minus a delta x. Okay, so, I have moved a distance delta x. That means that delta u1 is equal to minus a times delta x. Delta u2 is equal to 0. Okay, delta u1 is equal to minus a delta x and delta u2 is equal to 0. If I move a small distance minus delta x, if I move a small distance delta x in the minus x1 direction to this location, okay, this is once again delta x, I have moved in the minus x1 direction, delta u1 is equal to 0, delta u2 is equal to minus a, because the distance delta x1 is minus delta x. Okay, so, I get a velocity vector like this. And if I go in the minus x2 direction, equal distance delta x, okay, if I go in the minus x2 direction, equal distance delta x, then delta u1 is equal to plus a, because I have gone delta x2 was minus delta x. So, delta u1 will be plus a times delta x, and I get a velocity vector like this. So, you can see the antisymmetric part of the rate of deformation tensor corresponds to a rotational flow around this. Okay. It is in fact a solid body rotation, because the velocity, the relative velocity of nearby points increases linearly with distance from the origin. The relative velocity of nearby points increases linearly with distance from the origin. Okay. So, at this point I will get a velocity like this here, and here it will be still larger. Okay. And similarly in all of these directions. Okay, it increases linearly from the origin. That means that this represents a solid body rotation, okay, around the origin. No surprise, we had associated vorticity with the angular velocity of the fluid around a local around a point. Okay. So, this antisymmetric part of the rate of deformation tensor represents the local rotation, rotational motion of the fluid around this point. Isotropic part is the radially outward flow, antisymmetric part is the local rotation. Okay. In fact, you can relate the antisymmetric part of the rate of deformation tensor directly to the vorticity. We know that the vorticity omega I is equal to epsilon I j k d by dx j of u k, okay, del cross u. Okay. Now, I can use a symmetry transform to write this also as, rather than, I have two repeated indices here, j and k. Okay. They are repeated, they are summed over 1 to 3. So, I can very easily interchange j and k, and the result will be the same, okay, because j and k are just indices that are summed over, they are dummy indices. So, I can interchange the indices to get exactly the same result. Okay. So, this is also equal to epsilon I k j partial u j by partial x k, because I can interchange these two and the result remains the same. Okay. So, omega I is equal to this one, it is also equal to this one. So, I can very easily write it as half the sum of those two. Okay. If some quantity is equal to a, it is also equal to b, it is also equal to half of a plus b. Okay. So, therefore, I can also write omega I as half of epsilon I j k partial u k by partial x j plus epsilon I k j partial u j by partial x k. Okay. However, epsilon I k j is equal to minus of epsilon I j k, because when I interchange two indices in this antisymmetric tensor, I get the negative of the result. Okay. So, I can also write this as half epsilon I j k into partial u k by partial x j minus partial u j by partial x k. Okay. Now, I have defined for you the antisymmetric tensor Aij as partial ui by partial xj minus partial uj by partial xi. Okay. So, therefore, the vorticity is related only to the curl acting on, I am sorry, the cross product acting on the two components of the antisymmetric tensor, epsilon I j k times A k j. Okay. So, the vorticity can be related directly to the antisymmetric part of the rate of deformation tensor. Vorticity does not depend on any other part. It does not depend upon the isotropic part, because with the isotropic part it will be 0. For a symmetric tensor, if I take the vector minus its transpose, I will get 0. So, the only one that is left is the antisymmetric part of the rate of deformation tensor. Okay. So, the antisymmetric part of the rate of deformation tensor represents rotational flow. Okay. The axis of rotation is perpendicular to the plane of rotation. Okay. The plane of rotation is given by this antisymmetric part of the rate of deformation tensor. Therefore, the axis of rotation is perpendicular to the plane in which this antisymmetric part rests. Okay. That is the second part. First, isotropic, which we just done here, radially outward motion. Okay. Out of these three, this is the isotropic part. It represents radially outward or inward flow. It is proportional to the divergence of the velocity. Okay. Second is the antisymmetric part of the rate of deformation tensor. Okay. It represents rotation, solid body rotation about this center point, okay, about the origin of this coordinate system. Tells you how nearby points are rotating around the location at which you are sitting. Okay. It is related to the vorticity, okay, the curl of the velocity at that point. Okay. The antisymmetric part of the rate of deformation tensor can be written directly in terms of the curl of the velocity. The third part is the symmetric traceless. Symmetric traceless part. Okay. For this one, delta u1, delta u2, this is symmetric and it is traceless. Okay. So, there are different ways that one can write this, but you get the same type of deformation regardless of which way you write it. Okay. So, this is equal to 0, a symmetric tensor. So, a symmetric tensor. I have set, of course, the sum of the diagonals has to be equal to 0. I have set the diagonals themselves individually equal to 0, but that is not there is no loss of generality there, because I can always rotate my coordinate system in such a way that the diagonals become 0. I will discuss that a little later. Okay. So, let us see what kind of deformation that represents. Okay. So, in this case, delta u1 is equal to s times delta x2, delta u2 is equal to s times delta x1. Okay. So, this is x1, x2. If I go a small distance delta x in the x1 direction, delta u1 is equal to 0, because delta u2 is equal to 0. I am sorry, delta x2 is equal to 0. Therefore, delta u1 is equal to 0. Delta u2 is equal to plus s times delta x2. Okay. So, you get something that goes like this. If I go a small distance in the x2 direction, okay, if I go a small distance in the x2 direction, then delta u1 is equal to plus s times delta x2, okay, and delta u2 is equal to 0. Okay. Delta u1 is equal to plus s times delta x2 and delta u2 is equal to 0. When I go in the minus x1 and x2 directions, the directions of these arrows are reversed. Okay. That is quite easy, because I go minus delta x1, then delta u1 is equal to 0, delta u2 is equal to minus s times delta x2, okay, and this one. Okay. You can do it at various other intermediate directions. Okay. So, in this direction, along the 45 degrees in this direction, you will have outward here, and along the 45 degrees in this direction, you will have inward here. Okay. So, this is called pure extensional strain. Okay. This is called pure extensional strain. Okay. So, in this particular case, you can see that if I had a volume of fluid that initially looked like this, okay, if I had a volume of fluid that initially looked like this, is getting stretched along the plus 45 degrees and is getting compressed along the minus 45 degrees. Okay. So, after some time what it will look like is something like this. Okay. The axis remain the same because I have taken out the rotational part. So, the axis do not rotate. Okay. So, the axis remain the same, gets stretched along one direction, compressed along the other direction in such a way that the axes are not rotated, and secondly there is no expansion in volume, okay, because the expansion in volume was related purely to the isotropic part. So, there is no expansion in volume here, there is no rotation, this is pure extensional strain. Okay. This is pure extensional strain, there is no extension and there is no rotation in this case. In a fluid, we will see a little later that a solid body rotation cannot generate internal stresses, because when you take an object and rotate it, if it is a solid body rotation, the distance between nearby points has not changed at all. There is no extension or compression of distance between nearby points. So, the stresses that are generated cannot be due to the solid body rotation. Okay. So, the antisymmetric part of the rate of deformation tensor cannot generate a stress. If the fluid is incompressible, the isotropic part also is equal to 0, because there cannot be volumetric expansion or compression if the fluid is incompressible. The only part that will generate a stress is this extensional strain, the one that does not cause any rotation. Okay, the part, of course, the total fluid velocity field is the superposition of all of these three. I have separated out into three parts, one of which is radially outward or inward, the isotropic part. The other is the rotating part, okay, that is the antisymmetric part of the rate of deformation tensor, and this is the third part. And it is only this part that can generate a stress, because it is this one that affects the relative position between nearby points in the fluid. So, this was for 2 dimensions. Exactly the same can be extended to 3 dimensions. Okay. So, let me just explain to you how that is done. Okay. So, if I had a general 3 dimensional velocity field, okay, partial ui by partial xj, okay. This I can divide into 3 parts. One is aij, okay, plus the isotropic part is actually equal to, okay, 1 by 3. Okay. In 2 dimensions it was 1 by 2, but in 3 dimensions it is 1 by 3 del dot u times the isotropic tensor plus Eij. Okay. Eij is an antisymmetric tensor and Eij is a symmetric traceless tensor. Okay. So, for example, if I had this this was my rate of deformation tensor. The trace of this in 3 dimensions is equal to partial u1 by partial x1 plus partial u2 by partial x2 plus partial u3 by partial x3, okay, which is the divergence of the velocity in 3 dimensions. Okay, that is the trace of the tensor. Okay. And in order to make my tensor traceless, what I need to do is to subtract out 1/3 of this from each of these diagonal elements. Okay. In order to make it traceless, I need to subtract out 1/3 of it from each of these elements. Okay. And that is the reason I have this 1/3 here instead of half, okay, because if I subtract out 1/3, I get partial u1 by partial x1 plus partial u2 by partial x2 plus partial u3 by partial x3, and I have subtracted out 1/3 from each of them. So, it adds up to 1 and I will get something that is traceless. Okay. The easier way to see it from tensor notations. Okay. If I have Okay. If I have partial ui by partial xj, okay, is equal to aij plus eij plus 1 by 3 del dot u delta ij. Okay. What is the trace of this tensor? The trace of this tensor is the sum of the diagonal elements. Okay. The sum of the diagonal elements is given by, okay, partial u1 by partial x1 plus partial u2 by partial x2 plus, okay, this is equal to partial ui by partial xi. One repeated index summed over I is equal to 1 to 3, no unit vectors. Okay. So, that is the trace. This also I can write it as delta ij times partial ui by partial xj, delta ij times partial ui by partial xj. Okay. So, to get the trace of this tensor, you dot it with delta ij. Okay. Two repeated indices, you end up with a scalar. Okay. So, let us see what you get here. Okay. Delta ij times partial ui by partial xj is equal to delta ij aij plus delta ij eij plus 1/3 del dot u delta ij delta ij. Okay. Delta ij times aij, a is antisymmetric, delta is symmetric. If I multiply a symmetric and an antisymmetric tensor, okay, if I take the double dot product, you will get 0. Okay. If you take the double dot product of a symmetric tensor with an antisymmetric tensor, you will get 0. It is quite easy to see. Okay. You can just expand it out and work it out. Okay. So, this becomes 0 plus this delta ij times eij, I just add up the diagonal parts. Okay. So, when I have a summation delta ij times eij, this summation I is equal to 1 to 3, j is equal to 1 to 3 of delta ij times eij. That means that in one of the summations, I could have replaced I by j, because you get a non-zero result only when I is equal to j. Okay. So, this becomes E I plus 1/3 del dot u. Delta ij times delta ij is just delta I, because it is non-zero only when I is equal to j. Okay. What is delta I? Delta I is delta 1 1 plus delta 2 2 plus delta 3 3. 1 plus 1 plus 1, that is 3. Okay. So, this becomes equal to 0 plus EII plus del dot u. Okay. On the left hand side also, I have delta ij times partial ui by partial xj, which is basically equal to partial ui by partial xi. Okay. Left hand side I have del dot u, on the right hand side I have the trace of E plus del dot u. Okay. So, these two will cancel out to give me the trace of this is equal to 0. Okay. The trace of this is equal to 0. So, this is symmetric traceless, this is antisymmetric, and this is the isotropic part. Okay. The sum of the diagonals is equal to the divergence of the velocity times 1/3 of the identity tensor in 3 dimensions. Okay. So, this part here of course represents radially outward flow. It is not a 2-dimensional outward flow, but rather a 3-dimensional. Okay. From a point you have fluid coming out in all 3 directions. Okay. So, that is the isotropic part of the rate of deformation tensor. The symmetric traceless part represents a solid body rotation. Okay. The symmetric traceless part, I am sorry, the antisymmetric part represents a solid body rotation. Okay. So, the second part, so this is 1/3 del dot u delta ij. This aij represents the solid body rotation around this point. Okay. It represents a solid body rotation around this point. Okay. We saw that the vorticity vector omega I is equal to half epsilon I j k a k j. Okay. The direction of the vorticity is the direction around which there is a rotation. Okay. So, the direction of the vorticity is basically equal to half of epsilon double dotted with the antisymmetric part of the rate of deformation tensor. So, if this rate of deformation tensor is in some particular plane, the vorticity is perpendicular to that. Okay. And this AJK gives me the vorticity direction, solid body rotation about that. Okay. And this third part is a symmetric traceless tensor. Okay. So, let us just look at that. Okay. symmetric traceless, okay, Eij. Okay. Okay. I can write it as E11, E12, E13. Okay. And this is symmetric, therefore, E12 is equal to E21 and E13 is equal to E31. It is important to note that. Okay. Symmetric tensor, the sum of the diagonals is equal to 0. Okay. So, this symmetric tensor has 3 eigenvalues. Okay. It is a third order tensor. So, it has 3 eigenvalues. Okay. 3 eigenvalues which are real. Okay. So, it is a symmetric tensor. You know that if the tensor is equal to its transpose, its eigenvalues are real, and 3 orthogonal eigenvectors. Okay. That is 3 orthogonal eigenvectors. In addition, since it is traceless, you know that the sum of the eigenvalues has to be equal to the sum of the diagonal elements of the matrix. Okay. Since it is traceless, the sum of eigenvalues is 0. Okay. So, therefore, you can have either 1 positive and 2 negative eigenvalues, 2 positive and 1 negative, or you can have 1 0 and 1 positive and 1 negative eigenvalues. Okay. If you have 1 positive and 1 negative eigenvalues, it means that there is extension along one direction and compression along one direction. Okay. So, if I have 1 positive and 1 negative and 1 0. Okay. If I have 1 positive, 1 negative and 1 0, I have extension along one direction, compression along the other direction, and there is no deformation in the third direction. Extension along the direction on which the eigenvalue is positive. You know that the eigenvectors have to be orthogonal. So, the direction corresponding to one eigenvalue has to be perpendicular to the direction corresponding to the other. So, this is plain extension, extension in one direction, compression in the other direction, and there is no flow in the other direction, third direction. The second one is when there is 1 positive and 2 negative. In that case, you have extension along one direction and compression along the 2 perpendicular directions. Okay. So, this is called a uniaxial extension. Okay. So, if I just try to plot it here. Okay. These are my 3 axes. I have one direction extension and I have fluid coming in the other 2 directions and stretching along the third direction. So, that is called uniaxial extension, 1 positive and 2 negatives. And on the other hand, if I have 2 positive and 1 negative, it is the other way around. Okay. There is stretching along 2 directions and there is extension along the third direction. Okay. So, that would look something like this. Okay, I have stretching along 2 directions. That is biaxial extension. You cannot have all 3 positive because then the sum of the eigenvectors would not be equal to 0. So, these are the different kinds of deformation that are represented by this rate of symmetric traceless part, uniaxial extension, biaxial extension or planar extension. And that comes out of the fact that it is a symmetric tensor. Eigenvectors are orthogonal and eigenvalues, the sum of those is equal to 0 because it is traceless. So, these in brief are the types of deformation that can take place. Okay. And our next step is to relate the stresses to the different deformations that can take place. We will briefly review this before we go on to derive the momentum conservation equations which depend upon these rates of deformation. So, we will continue in the next lecture.